Okay, let's pick up with video number 2 for this week, where we left off yesterday. So, for the high pressure fuel system, newer electronic engines are what's called drive-by-wire. So there's no mechanical linkage between the throttle pedal and the engine. It's all electronic, done through the computer. So that's referred to as drive-by-wire. So if you see that term in the book, that's what they mean. So we've got two sensors that goes along with this fuel metering and other things as well. So we got a crankshaft position sensor and a cam position sensor. So the crank's main job is it picks up the little accelerations and decelerations of the crankshaft when the cylinders fire, so it knows if a cylinder is doing its job or not. And it gives us the RPM and indicates when cylinder number 1 is at top dead center. But as far as the injectors, they need to work with the camshaft, so they only inject fuel on the compression stroke. So the cam position sensor tells when to fire the injector for each cylinder, so it's going to be higher up and working off the cam. So the crank sensor is monitoring, and if we do a cylinder performance test with a scan tool or a laptop, then it's going to tell us what percentage each cylinder is doing when it fires. So it checks how much it speeds up and then slows right back down. We don't really hear it, but the computer can sense that. So it will tell us which cylinder is not contributing. So cylinder contribution test is a type of cylinder performance test to tell what it's doing. We talked about the adaptive idling, so here it will tell us if we had a cylinder that's not doing its job, but the cylinders on each side do a little more work to compensate for that. So it's kind of what this graph is showing. Cylinder 2 and cylinder 4 are not doing as much, so the cylinders on before and after that do a little bit extra to smooth out the idle. That's adaptive idling. And then the cam is basically saying how long the injector stays on. So you can see here milliseconds if you follow along on the PowerPoint. And on this video you can't really see it, but it'll tell you how many milliseconds the injector is on. That's how it meters the fuel. Metering and idle adaptation. Cylinder firing order and stroke are determined by sensors on the crank and cam that we just talked about. Camshaft, you can see you have a double here. That's how it knows number 1 is at top dead center and ready to fire. And if you look at this, it's in the firing order. They put their arrow on here backwards, but it's 15, 36, 24. So that's how it knows when to fire each injector off of that. And then the crankshaft, we know spins half as fast as the cam. Sorry, twice as fast as the cam. So it has a reluctance wheel around the outside here. Okay, so on the cam sensor, this is the reluctor wheel that is normally on the camshaft gear, and then you have the sensor that's reading these little windows, and the windows are different sizes so that it knows which cylinder that it's looking at to fire. And also remember that almost all computer systems run off of a 5-volt reference signal. That way it stays a constant 5 volts and doesn't fluctuate with the alternator changing voltages. So VREF is always 5 volts on most all computerized vehicles. That's automotive and big trucks as well. So if our metering is not right, it affects emissions. So uneven cylinder pressures can create excessive emissions such as NOx, hydrocarbons, particulate matter, and CO. Fuel metering can be adjusted through adaptive balance, so it can change each individual injector to try to fix the balance problem and get all the cylinders contributing evenly. Metering and calibration codes. So injectors are not all the same. They can make a perfect injector, but the cost would be astronomically high. So what we do is get it in the ballpark of we want it to do this, so we have a plus or minus on that. So then after they build the injector, they do a flow test on it basically and say we wanted this much output, it was a little bit light or a little bit heavy or just right, so they attach a code to that so the computer knows if that's a normal flow injector, a little bit light flow, or a heavy flow injector, and it can adjust the milliseconds based on that to get the right amount of fuel on. So a heavy flow injector may stay on a shorter amount of time than a light flow injector to inject the same amount of fuel. So here's a little graph in the PowerPoint that shows that cylinder 1's normal, cylinder 2's high, cylinder 3's a little bit, cylinder 4's low. So each one of those has a code on the injector itself. So when we replace an injector, we have to put a code for that injector into the ECM so that it knows what it needs to do time-wise to adjust for the flow rate of that injector. So you can't take injectors and like swap them to another hole when you're hunting a misfire. If you tear an engine down and just pull all the injectors and throw them in a big pile and don't mark where they go, you'll have to reprogram the computer when you put the engine back together and put all the codes in. Failure to enter an injection calibration code equals a rough running and possibly a fault code on your engine because the computer has the wrong information for that injector. Troubleshooting misfires. We do a cylinder cutout test now on the electronic engine. So way back in the day with the mechanical distributor pump, we could just take a wrench and loosen an injector line off while the engine was running and see if it changed the RPM to know if that cylinder was firing, and we could locate a misfiring cylinder that way. We would run across a line that we break loose and there was no change. We would know that that's the cylinder we're having problems with. We can't do that now with the electronic one, so the scan tool or computer will allow us to go in and turn the injectors off one at a time and listen to the idle. It'll also give us a bar graph as to how much it affected. So basically we can kill cylinders or cancel them out one at a time with the computer. Do remember that common rail, which we'll cover next week, do not crack those lines loose with the engine running because it's very dangerous to do so. So you have to use an electronic tool to diagnose those type of injectors or cylinder misfires. So like I said, it's a little bit hard to see on here, but here's the cylinder cutout. You'll be able to click on a cylinder one at a time with the device and basically turn that injector off, and it'll tell you how much RPM change on the engine was. Just keep in mind that with adaptive idling, you'll see it change and then start leveling out because the computer will kick in and start changing the RPM with the other injectors. So you'll notice it change over time while you got it canceled. Cylinder balance test we talked about measures crankshaft velocity for each cylinder, compression and power stroke. So same thing, we've got a service tool, electronic service tool that we can run that test, and it will help us identify which cylinder has the problem when we have a drivability problem. Okay, so let's get into injection timing now. One of the greatest things that all this computer stuff has done is we have infinite control over injection timing. We were kind of limited to a window back when we had mechanical pumps or unit injectors, we could change the timing a little. But now that the computer is controlling that injector, we can change injection timing, throughout the spectrum. It's made it a whole lot better to make the engine run smoother, quieter, more efficient, get better fuel mileage, because we have infinite control over when the timing occurs, and the timing has to change constantly based on engine operating conditions. Remember, we on our peak cylinder pressure should occur approximately 10 to 15 degrees past top dead center. So for that to occur, we need to be able to adjust exactly when we start injecting the fuel to get the end result to be 10 to 15 degrees past top dead center. Variables affecting timing: temperature of fuel, temperature of the intake air and mass of air, coolant temperature, engine oil, boost pressure, EGR rates, load, and RPM. All those things factor into the injection timing. So we have to have an ignition delay period. So ignition delay is the amount of time between the injection starting and the fuel igniting. So pre-ignition temperatures in the cylinder affect the timing. We'll get into that in a couple of slides. Fuel droplet sizing, so how much the fuel pressure coming out the injector is. The fuel properties, combustion chamber turbulence, and EGR gas in the cylinders. Engine load and injection timing increases the cylinder pressure as temperature speed up combustion. Loads increase, you need to add more fuel. Obviously, it's going to take more fuel to get the work done. Increased temperatures and pressures equals decreased combustion time. So the hotter the cylinder is, the faster the fuel is going to ignite. So a heavy loaded engine, it's got more temperature in the cylinder. We inject the fuel later to make sure we get combustion, or the highest cylinder pressure at 10 to 15 degrees after. So we have to monitor that with the computer and change the basically injection timing to have that occur right. Timing must be retarded or delayed when loads increase, so that's what I just talked about. When you have a heavy loaded engine, cylinder temperatures are going to be higher, so the fuel's going to ignite faster, so we have to inject it later or delay or retard the timing versus a non-loaded engine. Okay, if you look at this slide on your CDX, 1500 RPM full load's the fastest combustion speed, so we're at 5 degrees before top dead center. 1500 RPM medium load, we're at 10 degrees when we start the injection before TDC. And slowest combustion speed, 1500 low load, we start at 15 degrees. So the end result is the same. It's just the computer's monitoring to figure out how long it's going to take the fuel to ignite and change the timing accordingly. So lower speeds equals less fuel, lower cylinder temperatures and pressures, so a longer combustion time. Injection must be advanced at light load, so we advance it at light load, retard it at heavy load on the timing. As engine RPM speeds up, injection event must occur earlier, so we have to advance the timing as RPM increases. Injection timing and cold starting. Cold engines and low ambient air temperatures means longer ignition time, so we have to advance the injection timing in cold conditions. During cranking, though, injection must be retarded to allow more time to heat the compressed air. So while it's cranking, I know that sounds like that just contradicted itself, but while it's cranking, we retard the timing to allow more heat to build in the cylinder. Once it starts, we advance the timing because the engine's cold and the cylinder temperature is going to be lower. So it's going to be retarded timing while cranking with cold engine, advanced timing after the engine starts on a cold engine. We'll pick back up tomorrow.